Okay, let's see here. Let's do a couple. Sure, let's talk about that. Let's see here. Oh, I wrote the wrong thing earlier. 16C. Today is April 17th. Let's start there. Let's talk about spheres for another minute. Let's find the equation of the sphere with diameter endpoints. What do we got here? Let's see, -2, 5, 1, and 4, -3, 3. So whenever you're trying to find the equation of a sphere or a circle, we really only need to know two things. We need to know the center and the radius. Just kind of like how if you're trying to find the equation of a line, you only need two things. You need the slope and a point. Any point will actually do, it doesn't have to be y-intercept, but y-intercept's the nicest. So we need the center and the radius. And let me touch. You can see that all right? Okay. So first we're going to find the center. And since these 2 points are the endpoints of a diameter, we can just take their midpoints. When I think of midpoint, I just think of average. Right? The midpoint of 2 points is the average of those 2 points. So it's going to be -2 plus 4 divided by 2 for the x-coordinate, 5 plus -3 divided by 2 for the y-coordinate, and 1 plus 3 divided by 2 for the z-coordinate. Simplifying that, that's going to be 1 comma, wow, that's kind of boring, but 1 comma 1 comma 2. Not boring, just I like to have things different. Then to find the radius, you can do it one of two ways. You can either find the distance between your diameter endpoints, which is the length of the diameter, then cut it in half, or find the distance between your center and either one of those endpoints to find the length of the radius. I kind of like doing it the second way, personally. Yeah, so if I'm going to find my radius, I'm going to find the distance between my center and either one of those other 2 points. Between 1, 1, 2. If either one of these didn't have any negatives, I pick that one, but since they both have negatives, it doesn't really matter which one I pick. I'm going to pick the second one for -3. That's going to equal square root of 1 minus 4 squared plus 1 minus -3 squared plus 2 minus 3 squared. Simplifying that out, we get, let's see, the square root of -3 squared is 9. 1 plus 3 is 4. 4 squared is 16. And -1 squared is 1. Square root of 9 plus 16 plus 1, which is the square root of 26. Which doesn't simplify any further. Yeah.
In starting like grouping for like, because you used 4, -3, and 3, so you could have used -2, 5.
Yeah, exactly. So just to actually point that out, if I did the other one, the distance between my point and the other end point of the diameter, -2, 5, 1, should give us the same result. Let's check. That distance is going to be the square root of 1 minus -2 squared plus 1 minus 5 squared plus 2 minus 1 squared. And you'll notice that each of these actually is the opposite sign before we square them. Here it was -3 squared. Here it's going to be +3 squared. Here it was 4 squared. Here it's going to be -4 squared. And here it was -1 squared. Here it's going to be 1 squared. So that should always work out to be the same no matter which point you pick. Yeah. And just to kind of point out why it's better to do it this way. If you did it the other way and found the distance between this and this, the distance between those two would be the square root of 104. And then cutting that in half, square root of 104 divided by 2, it's just a little more work to actually like factor out the square number and divide by it. So I recommend doing it this way. And we're not done. They said to find the equation. So we have to take our center and our radius and then write the equation. So our equation is going to be, what do we have here? Let's see. X minus the x coordinate, which is 1 squared, plus y minus the y coordinate, which is also y minus 1 squared, and then z minus the z coordinate, so z minus 2 squared is equal to I could write the square root of 26 squared, but it's probably easier just to write 26. That is the equation of our sphere. Centered at 1, 1, 2, radius of square root of 26. The way I always kind of think about it is if you plugged in the center point, the left side of this equation would be 0. It's not a solution, but that's what you would get. Yeah, sure. Oh yeah, let's talk about that for just a second. As is usual, if you have questions along the way, please don't hesitate to ask them. Yeah, just starting with Celeste, Lexi, Amber, Ryan, Josh. Ryan, for some reason, always I'm like, I know it's Ryan, but let me make sure. Yeah, cool. I had this one. Yeah. So here's a question that I kind of saw as a homework question. I think it's worth checking out for just a second. So find the values of K. Where'd you go here? So that the following two planes, and our planes are 2x minus 5y plus kz equals 7, and negative 6x plus 15y minus 12z equals, it doesn't really matter, but equals 13. Want to find the value of k so that those are parallel. So for two planes to be parallel, basically the coefficients of x, y, and z have to be in proportion to one another. So in this plane here, I can see that the coefficient of x is a in this plane here, the coefficient of x is a multiple of that by -3. And the same thing here, 15 times or -3 times -5 is going to be 15. So for the z coordinate, the coefficient of k times -3, I should write that down. K, the coefficient times -3 needs to equal -12. And so solving for k, I'm going to get k equal to 4. So 1 second, right? What I would say is that if two planes are parallel, you can multiply all the coefficients by the same thing to get the coefficient in the new plane. So each of these coefficients, 2 times -3, -5 times -3, and 4 times -3. If we multiply them by -3, you end up getting the coefficients here. Doesn't work for the last. I will point out 7 times -3 is not 13. Question, Ryan. Cool. So it's kind of like how when two lines are parallel, they have the same slope, but a different y-intercept. When two planes are parallel, you have kind of the same slope coefficients of your variables and a different intercept or constant they're equal to. Similar idea.
Why did you do it equal to -12?
Oh, because it's a -12 right there. Yeah, so we do have to be mindful of all the constants. You could have, if you really wanted to, sometimes people do, I don't love this, but some people might write this as parentheses -6x plus 15y plus -12 in parentheses times z, just to make it more obvious what the coefficients are. I don't think that's super necessary, but yeah, we did need this coefficient to be 4, so that when you multiply it by -3, you got that, which is -12. Now, the second part of this, which is weirder, is are perpendicular. And honestly, without vectors, I don't know how to do this until I look in the book. Because in the book, if you look at problem 13 in section 7.2, they give you specific conditions for planes being parallel and perpendicular. So they even write the planes are, in fact, let me just show you. Maybe you can read this out. That's maybe. So let's point out, they say that planes are parallel if there exists a non-zero constant k such that the coefficient in the first plane is k times the coefficient in the second plane. And the same thing for B1 and B2, the same thing for C1 and C2. So all the coefficients in the first plane have to be multiples of the coefficients in the second plane, which is what we just did. And then the other thing they say, which I didn't really know this, but the problem says look it up in the book, that if you want planes to be perpendicular, all the corresponding coefficients multiplied together and then added up have to equal 0. So really, I don't actually know that in my heart, I just know that I read it in the book and they said it was true. So if I'm trying to then figure out what K needs to be to make these two planes parallel, I'm just gonna say, okay, great. This times this plus this times this plus this times this, and I do need to pay attention to the signs, has to equal 0. Well, I can definitely do that arithmetic to solve for K. So 2 times -6 is -12. -5 times 15 is -75. And -12 times K equals 0. I'm going to add 12K to the right. And then -12 plus -75 is -87. I'm going to divide by 12 and get K equal to the not very nice number, -87 over 12. And even though that seems a little weird to me, because I don't really know this, I know I can do the math that they told me to do. Gosh.
So you gave us like the rule for perpendicular. What was like the?
Sure. So yes. So in fact, let me write it down. So I really don't think you need to memorize this at all, but just so you can see it and have seen it. I would, if I was trying to know this, I would just go look it up again later. But I will just point out that yes, if you have planes, here are two planes. Something times x plus something times y plus a constant times z equals some constant. And then the other plane, same deal, except now I'm using a2 times x, b2 times y, c2 times z equals some other constant. And to be parallel, basically all of the corresponding constants have to be the same multiple of each other. So a2 has to equal some constant times a1, and the same constant k has to be true for the rest of them. b2 has to equal k times b1, and c2 has to equal k times b1. In our previous problem, our constant k was -4. And then for perpendicular, just to spell it out, two planes are perpendicular if a1 times a2 plus b1 times b2 plus c1. Oh, that makes total sense to me now that I look at it. Times c2 equals 0. There's a reason that makes sense to me. It has to do with the dot product of the normal vectors being perpendicular to each other. But I don't think we end up talking about that in this class, so I shouldn't get too into it. Yeah, so planes can either they can be parallel, they can be perpendicular, or they can just intersect each other in a line. That also happens. Fine. Yeah, let's go. Yeah, fine. So let's talk about quadric surfaces for a few moments. Quadrics, can I spell this? I can. There's like 6 of them, 7 of them. Let me look in the book here real quick. Sure, there's 6 of them. Probably my favorite one is, well, okay, don't play favorites. Paraboloid. Paraboloid. The reason I mentioned this one specifically is because I often use this one as an example when we start talking about directional derivatives. Or what I should say, partial derivatives, really. A paraboloid, the kind of basic one that we usually default to is the one z equal to x squared plus y squared. That's everyone's favorite paraboloid. If you're graphing it in 3 dimensions, it has, well, let's talk about the traces. So the trace. So in case you haven't heard the word trace before, that's totally fine. When someone says the word trace, they just mean, what does this surface look like in a particular plane? Usually one of the coordinate planes, meaning the XY plane or the XZ plane or the YZ plane. Also, for those of you that haven't been in classroom before, I typically call it the floor, the XY plane, the wall the chalkboard's on, the YZ plane, and the floor, the wall to your left, the wall behind me, the wall to your left, the XZ plane. And I'm thinking of that corner down there as the origin. So I will often say, yeah, there's the XZ plane. So when I'm thinking about the trace, I'm just thinking, what does this paraboloid look like in the YZ plane, where x is equal to 0, or in the XZ plane, where y is equal to 0, or on the floor, where z is equal to 0. Well, the floor is actually not that interesting here. If we set z equal to 0, then you have x squared plus y squared equal to 0. And there's only one solution. X and y both equal to 0. So your trace on the floor is just the point that's the origin. Not super helpful when you're graphing it. Not unhelpful, just not super helpful. If we look at the trace in the XY plane, sorry, that's what I just said, the YZ plane where x equals 0, well, then I'm going to get z equal to y squared, which just looks like your normal upward opening parabola. There's my trace. Oops, except it should hit the origin in the YZ plane. In a similar way, if I look at the trace in the XZ plane where y equals 0, I get z equal to x squared. It looks virtually the same. So then the reason we talk about the traces is because we kind of try to overlap all three traces onto the XYZ coordinate plane to then try and get an idea of what the graph actually looks like. So what I'm really thinking about doing when I graph this in my three-dimensional coordinate system, say, okay, well, here's my trace in the YZ plane. And honestly, what I'm really going to do is I'm going to think about revolving it around instead of trying to draw the one in the XZ plane, because the XZ plane is like the hardest plane to draw in. I'm kind of thinking about what happens if you revolve this around. It's going to be kind of circular. And then here's maybe my trace in the XZ plane. So you've got parabolas in both the YZ plane against the wall and the XZ plane against the other wall. And just to go along with the idea, you can also talk about level curves, where you're essentially talking about if you go up higher, like what's happening at a height of 4. Well, if z equals 4, then you're left with x squared plus y squared equal to 4, which is what kind of graph? A circle. Which is exactly what we're getting, right? If you go up 4 high, you're just getting a circle at that height of 4. If you go up 9 high, you're getting a circle of radius 3. Or the higher and higher you go, the larger and larger circles get. So that's one kind of quadric surface that comes up quite often. And its kind of hallmark is that you have one variable equal to the squares of the other two added together. But you don't have a z squared here, you just have a z. You could also have x equal to y squared plus z squared. And that would open up along the x-axis. So kind of the one that's the odd man out is usually the axis of symmetry. And it's not a perfect kind of correlation, but that's often how I think about it. Like the one that seems kind of different than the other two, that's usually the axis things are happening around. So just to kind of, in fact, let me show you with nicer pictures, but just to kind of go in that same sort of direction, you could say, oops, wow, okay, different graphing stuff. So just to point out, you could totally graph, yeah, no, I don't. So here's z equal to x squared. Well, putting this on a book is not good. X squared plus y squared. And it looks exactly like what we're talking about, an upward open parabola. But if you change, so you're gonna have like x equal to, whoops, z, x equal to z squared plus y squared. Now it's a parabola opening along the x-axis. And if you have the y thing isolated, y is equal to z squared plus x squared, it's a parabola opening along the y-axis. Still the same shape, just kind of reoriented as to which axis is opening around. I mean, just because we're already there, I talked about this last class, if you have something like y equal to z squared, ooh, yeah, cool. Then you've got a, what do we call this? Not my favorite. We call it a cylinder. The cylinder, I know, right? It's dumb, but it's actually called a cylinder because essentially you're missing a variable. That's not the whole reason, but kind of you said, I've got this parabola, y equals z squared, and then x gets to just range over all the other values. So we do call this a parabolic cylinder. Or, I mean, there are other things, right? You could talk about. Yeah, we shouldn't get too caught up in that. I don't want to waste your time. So that's one type of quadric surface. There are 5 others. And yeah, how much time have we got? We got enough time. I actually talk about them very quickly because I do think it's something people sometimes get a little bit focused on. Or so the teachers want you to know it, but they never spend enough time teaching it to you, I feel like. So let's briefly talk about the quadric surfaces. So the cone. I will also say in your textbook, what version, what edition of the textbook do you all have? I guess it doesn't really, I mean, so I have the 7th edition. It's the same section. The page number might not be exactly the same, but in section 7.2, before the problems, there's this page in my book, page 468, 469, that shows all 6 quadric surfaces. We just talked about the paraboloid. Notice I didn't say elliptic paraboloid because I was drawing the circular paraboloid. The only difference between the elliptic and the circular is that your coefficients of x squared and y squared can be different. That's going to mean you're longer in one direction than you are in the other direction. Josh.
Are you gonna teach us all 6?
Probably not. And I don't know what kind of expectation there is as far as how much you know it. So I'm going to show it to you briefly, but not in too much detail. Because again, I'm trying to walk the balance of showing you enough that if it comes up later, you have an idea, but not so much that if it doesn't come up later, I've wasted your time showing you something you don't believe. So that's why I'm kind of doing the less dramatic version, that is not the elliptic version, but just the cone version. So when I think of a cone, I just wrote the word cone. Why would I write the word cone again? I think of, I do think of it. So I personally think of it as z squared equal to x squared plus y squared. That's the cone. That's the like everyone's favorite cone. We're usually drawing things around the z-axis unless there's a good reason not to. So this looks like cone. And it does literally go straight through the origin down to the bottom. Sometimes people point out that it's a double cone. You get the top and the bottom because you'll z be positive or be negative. It is a cone. And the thing I was kind of thinking about with this cone is if it's actually z squared equals x squared plus y squared, the amount you're going over is the same amount you're going up. Or kind of like a 45-degree angle deal. What else to say here? The way your book would probably write this is, they would write it as, which would they write it? Yeah. X squared plus y squared minus z squared equal to 0. That's the more general way, right? Because we often like to write all the variables on one side and constant on the other side. Why do we care about the cone? Well, the double cone, I have to say this, I can't not say it. You probably don't care. But the double cone is where all of your, oh my gosh, your conic sections come from. That might not mean a lot, but let me say, this double cone, if you cut it with a plane, you get all sorts of different usual shapes. Like, for example, if I cut this with a horizontal plane, I would get a circle. Right? If I go back to GeoGebra for just a second. I do think if you're trying to get an idea of how things look, GeoGebra is pretty useful. I think it certainly helped me visualize things before that I might not be able to visualize so easily. Sometimes it's not always super what I'm looking for. Cooperative. Wow. Oh geez. Okay, let's just try. Yes, let's do that. Oh my, sorry. Sometimes ooh, I don't like you. Go away. Okay, thank you. So someday we can graph this cone z squared equal to x squared. Oh, not the right button. Sorry, sometimes, it's hard to write the thing when you're not looking at the screen. Cool, and then tap on. Maybe someday ever, yes. Cool, there's our cone. And then if we cut it with a plane like z equal to 3, you get the circle. And it's definitely a circle. And if you cut it with like a slanty plane, like z equal to x, wow. Sometimes not my best. I don't know how I'm doing that. It's clearly magical. I wanted to do z equal to x plus 2. You get come up far enough. You get an ellipse. Oh wait, no, sorry. You get a parabola. So depending on what kind of plane you cut this double cone with, you get all the usual shapes. You can get a circle, an ellipse, a parabola, a hyperbola. Right? If you go, let me give you one more, and I promise. Well, baby, I try to make promises here. If you do something like the plane x equal to 3, yeah, then it's cutting through the top and the bottom, so you're getting a hyperbola. Anyway, that's where all those graphs come from: the hyperbola, the parabola, the ellipse, the circle. And Ryan, you wouldn't. That's why I said it's not that important. That's why I was trying to go through quickly, because I felt compelled to say it, because it's kind of a big deal, but no one's going to really ask you about these topics. So
This is just general stuff, right?
right, but I do want. So the kind of question someone asks you about these quadric surfaces is maybe how to graph them, or what the trace would look like, to identify the type of surface you have based on the equation. So here's what I've got so far. Z equals x squared plus y squared paraboloid. Z squared equals x squared plus y squared cone. And it doesn't matter if the z squared is here or the x squared here or the right. It's just if it was x squared equal to y squared plus z squared, then it would be the same sort of deal, except it's open along the x-axis. So it's a cone, opens along the x-axis. And then if you have different coefficients, things get bigger or smaller in one direction. Let's talk about so there's a few left. The other one you've already done, but I am going to be specific with it, is the ellipse. So you know the ellipse, you just know it as a sphere. Ellipse, or really, the ellipse is just the more general version. So here's an equation of a sphere. Center at the origin. With a radius of r. Going to be x squared plus y squared plus z squared equal to r squared. Or if you prefer centered anywhere, centered at the point h comma k comma j, it's just going to be x minus h squared plus y minus k squared plus z minus j squared equal to r squared. I don't think I need to draw it, because I can draw. You can watch me draw a circle, but I don't think it's going to be that illuminating to just draw a circle. What I want to point out, though, is that the hallmark of a sphere or an ellipsoid, ellipsoid, apologies. An ellipse is two-dimensional, an ellipsoid is three-dimensional. Just like a parabola is two-dimensional and a paraboloid is three-dimensional. And I know it does, wow, yeah, let me try writing that one more time. Ellipsoid. The hallmark here is that you have positive x squared plus y squared plus z squared. Every variable is squared, and they are all added together. And the only difference between a sphere and an ellipsoid is that the sphere, they all have the same coefficient, whereas an ellipsoid, they have potentially different coefficients. So an ellipsoid would look something more like x squared over a squared plus y squared over b squared plus z squared over c squared multiplied. And the reason they write it this way, which is annoying, is because it helps you graph the intercepts. If you write it this way, it's really easy to see that the intercepts are x is plus or minus a, y is plus or minus b, and z is plus or minus c. So writing it this way makes it easy to find the intercepts. If you wanted to, 1 second, right? I could say here's an ellipsoid, 4x squared plus 9y squared plus z squared equal to 1. Or let's make it 36. How do I know it's an ellipsoid? Because I know that I have x squared plus y squared plus z squared, but they all have positive coefficients and they're not the same. How would I draw it? It's actually not too terrible to draw. So I know it kind of has an egg shape, although it's a symmetrical egg, not like a lopsided egg like eggs actually are in the real world. So I was going to draw this. Really, I'm going to start thinking about the traces. Really, I'm just going to think about the intercepts. If I set x and y equal to 0, what am I going to get for z? Yeah, or -6. So there's my z-intercepts, 6 and -6. And if I set x and z equal to 0, my y-intercepts are going to be plus or minus 2. And if I set y and z equal to 0, my x-intercepts are going to be plus or minus 3. So I've got my trace in the xy plane is an ellipse. Although it looks kind of circular the way I drew it because it just happened. So one axis is a length of 2, one axis is a length of 3. And in the xz plane, also an ellipse. And in the yz plane, also an ellipse. So there's my egg-shaped looking ellipsoid. Kind of neat. But again, the thing I would point out is that for an ellipsoid or a sphere, x squared, y squared, z squared are always positive. You don't have a negative coefficient.
When you draw the ellipse, it runs through all those points.
Yeah. Or actually, when I draw the ellipsoid. And what I'm really thinking about is finding the 3 traces, right? My trace when z equals 0 in the xy plane, I'm just getting 4x squared plus 9y squared equal to 36, which gives me an ellipse that looks like having an x-intercept of plus or minus 3 and a y-intercept of plus or minus 2. Oh, and my drawing skills. So there's my ellipse in the xy plane. That's this one right here. And then I do the same thing for the YZ plane and the XZ plane. And I get those ellipses as well. And I kind of smash them all onto the thing at the same time and then try to draw the surface that encompasses them all. Again, I don't know how much of this you really have to do. So let's get to the last, the next two. So the reason I'm emphasizing here the nature of the fact that all the x squared, y squared, z squared are all positive is because the next 2 quadric surfaces, 1 or 2 of them is going to be negative. So let's draw the next one. And this is where I think the traces actually really come into play. We'll do that one first. So let's say we had, it's going to be a hyperboloid of 1 sheet. You know what? And I think I have a good handout somewhere that I'll post on Canvas as well about all this stuff because I think so hyperboloid of 1 sheet, you've got x squared plus y squared minus z squared equal to 1. That's the way it's usually thought of, or x squared over a squared plus y squared. The more all-encompassing way is x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. Well, let's keep it simple. So when I think of this, I think about, well, actually, I do think about the traces. So let's think about the traces for a moment. My traces. So if z equals 0, also I will point out z is the odd man out here. X squared has a positive coefficient, y squared has a positive coefficient, z squared has a negative coefficient. So we're probably gonna have symmetry around the z-axis because it's kind of the odd one out. Let's see what I mean. So z equals 0, I'm left with x squared plus y squared equal to 1, which is a circle, radius 1. So in the xy plane, circle of radius 1. Great. If I set y equal to 0, I'm left with x squared minus z squared equal to 1. And for whatever reason, this seems to be a graph that people are just less familiar with in general. But this graph is a hyperbola. If you start plotting points, I will point out that you don't have any z-intercepts. Because if x were 0, negative z squared can never equal 1, or z squared can never equal negative 1. So there's no z-intercepts. But if you set z equal to 0, x squared can definitely equal 1. You just get plus or minus 1. And then, as the x values get larger, the z values also get larger. For example, if x equals 2, then you have 4 minus z squared equal to 1. So z is going to equal plus or minus the square root of 3. So if x is 2, z is not quite as big as 2. It's a little less than 2. Or negative that. And that's true if x is 2 or negative 2. You kind of got a shape, and I'll just tell you it looks like this. Never my favorite graph to draw. Ooh, really not my favorite graph to draw. Yeesh. I've drawn better before. Yeah, that's not my best. But then I'll also point out that the other trace, when x is equal to 0, essentially gives you the same graph. If you set x equal to 0, you're going to get y squared minus z squared equal to 1. And if you graph that, it's going to look the same, except now it's the y and the z. It's going to do the same kind of thing. So then if you try and put this all on one graph, I'm not going to do that because I know it's going to look messy. I'm going to say, well, I know essentially I've got kind of circular thing going around here, and I'm just getting bigger and bigger circles like that. So here's my hyperbola of one sheet. I always think about this as an old reference. Well, not old, just still current, I guess. I mean, The Simpsons is still a show that is on TV. Have you ever watched The Simpsons? Ever seen the intro? I mean, or have you ever looked at a nuclear power plant? You know, like the cooling towers that have that kind of shape? That to me is the shape of a hyperboloid of one sheet. It kind of looks like the nuclear power cooling towers. So I usually kind of graph it like this. Poorly. If I want to draw my axes in here. And then you've got kind of here's your trace in the XY plane. And here is your trace in the YZ plane. And here is your trace in the XZ plane. Hyperboloid of one sheet. You got time. Okay, cool. Yeah, right.
Can you explain again why the parabolas?
Hyperbolas.
For what's the y equals 0 and x equals 0?
Like why we get that? Or like how?
Instead of a
Well, so typically you get a hyperbola when you have x squared minus the other thing squared. So if you graph like x squared minus y squared in 2 dimensions, you would exactly get this sort of shape. And really, so yeah, like for example, if I were to graph x squared, and let's do y squared minus x squared equal to 1. What I'm actually kind of thinking of just for now, again, I'll point out not a function, right? This graph here, definitely not a function. Fails the vertical line test all the time. but still a worthwhile graph. If you graph this, you get y squared equal to 1 plus x squared, or y equal to plus or minus the square root of 1 plus x squared. Which if that 1 wasn't there, would just be plus or minus x. So it's pretty close to plus or minus just x. In fact, this hyperbola has slant asymptotes at y equals x and y equals negative x. So I tried to do a good job of drawing it, which, see here, you get slant asymptotes like this. And let's see, if x is 0, y is plus or minus 1. And then if x is, say, 1, y is going to be plus or minus root 2. Root 2 is about 1.4. So I'm looking at like, I don't know, maybe like there-ish. So the thing is, right, we can see that as x gets larger and larger, the y values also get larger and larger, or closer and closer to that value. And really I'm saying x could be positive 1 or negative 1, because we're squaring it. So really, if x is 1, y is plus or minus root 2. If x is negative 1, y is also plus or minus root 2. And then I can keep going, right? Now it's a long process. The idea, right, if x was to be, say 2, y would be plus or minus root 5, which is a little bigger than 2. I'm over here at root 5. It's like that. So I'm going this way, like that, and doing the same sort of thing over here. It's getting closer and closer and closer to that slant asymptote. Same deal to the left. Do be careful if you ever have to draw this. They're not actually parabolas, because parabolas don't have slant asymptotes. Parabolas go more up. These ones go more out than up. But that's the idea. That's a hyperbola, and the standard sort of equation for hyperbola is y squared minus x squared equal to some constant. Or if it's x squared minus y squared, it opens right and left instead of opening up and down. Okay. I think I have enough time to get to the last two. So, hyperboloid of one sheet. I think of it, hyperboloid of one sheet, you have one minus sign. Hyperboloid of two sheets, you get two minus signs. So hyperboloid of two sheets, and you'll see why we call it that in a second. Just like an ellipsoid is a revolved ellipse, or a paraboloid is a revolved parabola, a hyperboloid is really just a hyperbola that you kind of revolved around the z-axis. Same thing here. It's still going to be the same idea, but now it's going to be z squared. Fine. I'm going to write it the way I want to write it. Z squared minus x squared minus y squared equal to 1. Or writing things in order, I guess you could write it as negative x squared minus y squared plus z squared equal to 1, but that just seems unnecessary to me. Oh no, actually, I take it back. They did it that way in the book. I'm shocked. They did z squared minus x squared minus y squared too. Cool. So here, yeah.
Does it matter which sides are negative?
Yes, in that if it matters which axis you're going to be centered around. So in this previous example, just to kind of go along with the whole usual theme, if instead our hyperbola of one sheet had been, say, like x squared minus y squared plus z squared equal to 1, same shape, but now centered on the y-axis. So this one would have, right, it would look like this. Well, now I'm trying to draw, so the cone actually goes through the origin, whereas here we're kind of bowing in, but we're not actually hitting the origin right there. If it was equal to 0, that's when you get a cone. So the difference in because let me say it this way. If this equation were equal to 0, then the origin would be a solution. 0, 0, 0 equals 0. But since it's not, you're kind of getting this degeneration in some sort of way. Okay. So hyperbola of two sheets, same idea, except now you're not taking, that's what I can say it that way. So last time what we did was we took this hyperboloid and we rotated it around the z-axis. Well, now we're going to take the other hyperboloid, the one that opens upward instead of the one that opens sideward. So here's what we're going to get. We're going to take this hyperboloid. Try and be smooth about it. Not that smooth. And there's the bottom half of it. So there's your trace in the YZ plane. I've set x equal to 0. I got z squared minus y squared equal to 1. And now I'm just going to revolve it around. And that's why it's called a hyperboloid of two sheets, because you've got this disconnection between the top half and the bottom half. So I don't have time to draw the traces at this moment, but I'll just point, well, I do. So XY plane. With the XY plane trace, it's fun. I definitely have time to draw that. Done. I drew it. There isn't one, right? If you try to find the XY plane trace, you set z equal to 0. You've got negative x squared minus y squared equal to 1. There's no solution there. Or if you prefer, x squared plus y squared equal to negative 1. No solution. There is no trace in the XY plane. And then, as mentioned before, in the YZ plane, the ZY plane, we would have x equal to 0. So you have z squared minus y squared equal to 1. So we're just getting that same shape. Sorry, I know that's not the best drawing I've ever done. And then in the XZ plane, same thing, right? In the XZ plane, you're just getting the same sort of trace. You're getting z squared minus x squared equal to 1. That's why the one that's the odd man out has the symmetry, because whether you set y equal to 0 here or x equal to 0 here, the equation you're left with is still essentially gives you the same graph. But then setting z equal to 0 is totally different. Okay, last one is my favorite one. Well, they're all my favorites. Yeah, the last one is a saddle. So the last quadric surface is a saddle. So called because it looks like a saddle, right? If you've ever seen like a saddle on a horse, or the saddle when you're out hiking, which is when you like hike up to like the top and you instead of going over the hill, you can go up either direction. That's also a saddle the same sort of way. So saddle, typical equation, z equal to x squared minus y squared. Was that my favorite one to draw? No, it's not my favorite to draw. But I'm going to draw, no, that's fine. No, I should draw. That's a saddle, but I'm gonna draw the one I'm better drawing because you know I like you guys. I like me too. So another saddle, z equal to y squared minus x squared. So generally for a saddle, you have one variable to the first, and then the difference between the other two squared. Now I should point out with all these equations, there's lots of other weird ways you can write the equation of a saddle. Technically, although you can explore this later, z equal to x times y gives you the same saddle, but rotated 45 degrees around the z-axis. Kind of cool. Anyway, let me draw it for you, and then we'll call it a day. So here's what I'm going to do. XY plane. Ooh, XY plane is not my favorite. You get y squared minus x squared equal to 0. You get y squared equals x squared, which is y equal to plus or minus x. Not super helpful. I don't recommend drawing that trace. But then the other two are good. X equal to 0, you get z equal to y squared. Y equal to 0, you get z equal to negative x squared. I'm not going to draw y. That. Okay, putting it all together. The z equal to y squared upward opening parabola in my YZ plane. I know we're out of time, but I really want to give you this picture before we go. If you need to leave, you're always welcome to leave. So here's my y equal to z equal to y squared. And then downward opening parabola in the XZ plane. So downward opening parabola, coming kind of this way. And then what happens is essentially in your level curves, so I know we didn't talk about very much, but if you let z equal like a large positive number, like if z is equal to 5, you've got a hyperbola. Y squared minus x squared equal to 5. Or if you let z equal to -5, you have a hyperbola. -5 equals y squared minus x squared. It's kind of the other way. So what happens is, like way up here, you've got a hyperbola opening to the right and to the left. And way down here, you've got hyperbolas opening in the x direction towards you and away from you. And then if you start connecting things up, my favorite part of drawing this, you get something that's like, oh yeah, I can kind of see the saddle-y shape there. There's your saddle. And you can imagine someone like literally sitting in that saddle and yeah, saddles are neat. So there's all 6 of your quadric surfaces. Did we waste most of our time today talking about them? I don't know. I mean, not really. You learn something, even if you don't ever get tested on it again. But I will say typically, at least what I've seen in web work before, not that you guys have web work, but I've seen questions where like you're given an equation and asked to identify what sort of quadric surface it is, whether it's a hyperboloid of 1 sheet, 2 sheets, or an ellipsoid, or a saddle, or paraboloid, or yeah, right. Yes, that's the way I think about it. There's 2 negatives. And really because the hyperbola you're kind of revolving around the separated part versus the unseparated part. Gosh.
Tell the shape of the graph by just the equation?
Yeah, that's kind of the idea. So looking back at the whole kind of page from this, and if you need to go, you're welcome to go. But an elliptic cone, it's always going to be one positive thing squared plus another positive thing squared, and then minus something squared. So there's one negative squared equal to 0. Elliptic paraboloid, just one thing to the first equal to the sum of the squares of the other 2. So z equals x squared plus y squared, or y equals x squared plus z squared, or whatever. Hyperbolic parabola. So why would you call that? Saddle. That's a saddle. I don't know why you wouldn't write that in there in the book. The hyperbolic paraboloid, it's one thing to the first equal to the difference in the squares of the other 2. So z equals x squared minus y squared, z equals y squared minus x squared, or x equals y squared minus z squared. Right? And whenever you're changing which one's on its own, you're just changing kind of which one's centered, which axis things are centered around. Ellipsoid, all the things are squared and added together. Equal to some number. It doesn't have to be 1 there, but this is like the standard. Hyperboloid of 1 sheet, you've got 1 minus sign. Hyperboloid of 2 sheets, you've got 2 minus signs. I don't know how much of this you really, but it is good to have an idea of what these surfaces look like, because what we're gonna do with this stuff next time, maybe the time after, is we're gonna talk about on a surface like this, how could you find where, say, the function is or a relative minimum, or a saddle point, because a saddle point, interestingly, is a minimum in one direction and a maximum in the other direction. That's actually why it's that's why it's actually important to talk about saddle points, because they are something we look for when we start talking about how to find the, say, relative minimum of a surface, or the relative maximum of a surface, or maybe the saddle point. That's where we're going with this. And so I think the idea is just to have some familiarity with the quadric surfaces, so that then when we start talking about where these relative extrema live, like, oh, that has some sensibility to it and not just seems totally bonkers.